Hello and welcome to our team's technical design project for Senior Design. The title of our project is Development of a Mobile Robot for Navigation Research. We are team number 41, and our team is composed of Joel Smith, Ethan Stallman, that's myself, Meng Wu, and Jinyi Li. Our advisor for this semester and next for our Senior Design is Professor Dieter van der Elst, and our project coordinator is Dr. Mark Cahay. So here's the table of contents, just giving a brief overview of what our presentation is going to look like, the structure of it. So I'm Ethan Stallman. I'll be talking about the problem description, talking about the problems that our project will be addressing, and also some of the benefits that will be obtained from completing this project. Joel will be talking about the design process, so some of the steps in the design, and he'll also talk about some of the components that we'll be using when we physically build the circuit and wire it up. Meng will be talking about some of the requirements that were laid out for our project, and also some metrics of assessment, which we'll be using as we go. And Jinyi will be looking at the design overview, so she'll be giving us some block diagrams and just showing us what the design will look like, and she'll also touch on some potential concerns we may have next semester moving forward. So getting started here with the description of the problem. So there are basically two problems that are being addressed here. First, at this point there is insufficient mapping information out there for mobile robots that have 360-degree vision. So there are plenty of robots out there, maybe applications of Arduino or Raspberry Pi that have programming built in for obstacle avoidance. So there are plenty of robots out there like that already, but there are none that we have seen that collect mapping data, which can be used in the future. So we'll be looking at that, and we'll also be looking at addressing our team's just overall lack of knowledge and experience in mobile robot design. So that was another reason to take on the project, was to just build on our knowledge. Some of the benefits of the project, as I said before, we'll be collecting data, mapping data, and we'll be, so once that data is collected, in the future projects we'll be able to create mapping algorithms to use this data effectively. So our project is going to basically be a stepping stone for future projects. And as I said before, another benefit of the project is to build on our team's knowledge of robotics and just enhance our overall learning experience in senior design. So some of the benefits of solving these problems that I've touched on the last slide. As I said, our project will be the basis for future projects and mapping algorithms. So we'll be collecting sonar and LiDAR data with our onboard computing device, and we'll be sending that to a host computer. And the data will be a basis for future projects, as I said. It'll help to increase movement efficiency, so when a robot is finding its way through an obstacle course, it'll be able to be more efficient moving from point A to point B. And as I said, create the mapping algorithms in future projects. For the overall learning experience, so we'll effectively be building a mobile robot from the ground up. This will include circuit design and also include wiring up all the different components and figuring out what it's all going to look like as far as building up the robot and the sensors and everything on the platforms to make it all one cohesive unit. And as we collect our data, we'll be relaying that data over Wi-Fi to a host computer. So getting more experience with sending data over wireless. And finally, there will be a lot of programming involved with this project. And we're all electrical engineers, so it'll be a good experience for us to look at the programming side of things as well. And now Joel will talk about the design overview.
We had a lot of requirements for this project that Meng will cover in the next section, but some of them are omnidirectional movement, obstacle detection and avoidance, and collecting mapping data. 360-degree vision, sonar data detection, and inertia measurement to provide odometry and compass measurements. So we will use omnidirectional wheels, as you can see in the picture here, to achieve omnidirectional movement with a servo motor for each wheel to make the robot move. We use a LiDAR camera, similar to the one that you see here, for obstacle detection and mapping. And we use a 360-degree camera so that if the robot is stuck, we can assess the situation and move the robot manually if necessary. For the board itself, we discussed several different types like Arduino, Raspberry Pi, and Miniboard. We decided to go with a Miniboard because it has an Intel processor in it and it can run Windows programs, so it'll be more versatile for what we use it for. And also Professor Vanderelst has a Miniboard that we can use, so that will make the project more cost effective. For the shape of the robot, we discussed using a 3-wheeled base because it would be cheaper because we would only need 3 servo motors instead of 4. But we decided to go with 4 instead because it would make the calculations easier when you have right angles for movement instead of a triangle. Then the 3-wheel base runs on 12 volts and we wanted to have everything run on 5 volts so it would simplify the wiring so we wouldn't have to step up or step down the voltage. For creating the base, we will most likely be using a CNC machine in the robotics lab to carve out the base, or we might just order one depending on which one is more cost effective. For communication with the robot, between the robot and the host computer, we'll be using a Wi-Fi dongle to connect them. Because another requirement is wireless communication between the host computer and the robot. And we'll go to Mang to talk about some of the requirements.
Hello, my name is Ming. I'm gonna be talking about the requirement and assessment metrics. And about this project, the requirements gonna include majorly 4 parts: the hardware assembling, the mobility, and the data mapping, and the wireless communication. First of all, the hardware assembly, and the mobile robot could need a platform or base to begin with. The base should contain the chassis with multiple mounting holes, 4 wheels, 4 servers for wheels, and battery slots, servo controllers, and a single board computer to attach on it. It requires all the elements to perfectly assemble to make sure the robot be able to run. And all the components will be attached on the chassis and we picked up, and all the wires and electronics will be connected to the board. And we have wheels and servers to run the robot. As my teammate mentioned before, we picking up the manual board instead of microcontroller is because it's compatible with more software. And another thing is we have 360-degree cameras connect to the board to provide more views. Next thing is mobility. We have to make sure the robot to run, and it has to be controlled by the host computers. The software we're going to use is Visual Studio, and which will be compatible with motherboard, and a certain circuit will be designed inside the motherboard, and we're also gonna program it to run the robot. And the 360-degree laser scanner will be on board we will program it to avoid obstacles. And more importantly, the robot has to be omnidirectional. It requires special wheels to do it, and it involves some calculations and programming. And next is data mapping and wireless communication. So the main objective for this project is to collect mapping data and send back to the host computer wirelessly. And we may have compass device to identify the direction, and we will be needing the sensors to collect data, collect and store data, and then we're gonna retrieve it and send it back to host computer. In order to do the wirelessly, we're gonna use Wi-Fi torch. Okay, in conclusion, here's the assessment metrics. So this robot's gonna have all the platforms gonna contain all the elements, and the robot has to be run omnidirectionally, and it also has to be able to avoid obstacles. And the most important thing is the robot's gonna be able to collect data and send it back to host computer wirelessly. So my next teammate gonna continue to talk about.
So this is a transparent box diagram of our design, showing how our robot works. Inside the larger square are single board computer, servo controller, servos, and sensors. The arrows indicate the direction of data transmit. And the host computer will send signals to the single board computer on a platform. Through the single board, sensors can be controlled as well as the servo controller. Then the servos can be controlled getting the robot to move. At the meantime, sensors will send data back to the single board computer, then to the host computer via Wi-Fi, so we can analyze the data and perform mapping. And here is a list of the parts we are going to use, with prices on the right. We are gonna need a miniboard max as cheap as $0 because Professor Venerist can lend it to us. And 3 chassis are listed in case we want to change the layout of our robot. A 6-channel micro maestro servo controller with a native USB interface and internal scripting control is listed also. And then we're gonna have a $50 micro leader module, which can detect the distance between obstacle and our robot. Wheels, servos, and other additional hardware will cost about $50. And everything mentioned above can be powered using 5 volts from a 4xAA battery pack. This was having to do onboard DC-DC conversion. The total cost is about $200. It's a conservative estimate. We may add sensors to fulfill other functions of a navigation robot. And also, there are some concerns about our project, since we are going to deal with the signals of sensors, servos, at the same time using the motherboard. Programming is a big problem. Besides, because the motherboard doesn't have built-in Wi-Fi connectivity, we will use a dongle instead to send and retrieve data. It will pose significant impact if we cannot handle this dongle. And for overall assessment, generally we are following our time schedule. We are going to order the parts we need before next semester, started to programming at the beginning of spring semester. And interface and platform building should be implemented before February. Then we will start to test our robot and debug at the same time. We will try our best to complete the implementation of our robot in March. So in the end, thank you for watching.
Like 1540.